Well, greetings out there in YouTube land and welcome to today's video, which is a long overdue part 2 to our capacitors video series. The remaining topics we'll cover will be a capacitor efficiency, how they can be wired in series versus parallel, how capacitors can differentiate between different frequencies, the specific application of capacitors in audio circuits, and how do electrolytic capacitors accomplish the hat trick of both having high voltage ratings and high capacitance. So without further ado, let's get started with capacitor efficiency. We learned in part 1 that an ideal capacitor stores and releases electrical energy with no absorption or loss. Which is ideal, but as in all things mechanical and electrical, no capacitor is 100% efficient. The efficiency of a capacitor is called its Q factor. I know this sounds like one of those shows on TV where they try to find the best singer or the best capacitor, but in this case it relates to imperfections that may occur within the capacitor, which will affect or reduce its efficiency. Now, we can designate or diagram this type of imperfection by showing a resistor in series with the capacitor. In other words, if an ideal capacitor has no resistor here and it is 100% efficient, then every bit of voltage which is applied to one side will appear on the other. But since we know that they cannot be 100% efficient, we can represent their inefficiency with a resistor in series with the capacitor, which will reduce the voltage seen over here and represent how inefficient the capacitor is. Now, there's a name for this imaginary resistor that we're placing in series with the capacitor to designate the capacitor's inefficiency, and it is called the equivalent series resistance, which we've all heard of as the ESR value. We have meters that can measure this value. I have one made by Anatech, which I have demonstrated in some videos. And we see that the value of equivalent series resistance increases as the capacitor ages and loses its efficiency. It's evident then that the lower this value is, the more efficient the capacitor is. When capacitors are first created, their ESR values are at a minimum. They're never zero. I've never seen one be zero because no capacitor is 100% efficient. But we'll see that as the capacitor ages, the ESR value will go up. And when it reaches a certain threshold point, we realize that the capacitor itself is no longer usable in our circuit. Another way to measure the efficiency of capacitors is the leakage, which is due to imperfections in the dielectric. And in this case, can be diagrammatically represented as a resistor in parallel with the capacitor. Now, when we apply alternating current to a capacitor, we see that an almost equal amount of alternating current will arise on the other side of the capacitor. Now, this makes it look as if alternating current can pass through a capacitor, but it really can't, and we'll see why in just a few moments. The other side of the coin, however, is when we apply direct current to a capacitor, and none of that direct current should be able to pass through. If it can, we can indicate the amount of leakage that the faulty capacitor demonstrates with this parallel resistor. While the ESR value can be measured by specialty meters, which are created just for that purpose. To measure leakage in a capacitor, you pretty well have to charge it up to its full operating voltage and then measure how much DC appears on the other side of the capacitor. That amount then will tell us what the leakage percentage is of the capacitor and whether or not it is suitable for our use. Particularly, this is important with coupling capacitors in audio circuits. Okay, now it's time for Rusty's most challenging scientific evaluation. I've got a box of Milk-Bone dog biscuits. They have 5 different flavors. One of them is turkey, and I couldn't find one that looked like the turkey. But we got bacon, beef, chicken, and sausage. Now here's the way it's going to work. I'm going to lay these down outside and turn Rusty loose. We'll let him sniff and see which one he picks. Now, and my theory is they're all exactly the same thing, just different colors. However, if he can pick the same one out, say 3 different times, then I'm going to start to believe that there's actually some difference in these dog biscuits. So get your money down on which one of these you think he's going to pick. Let's go outside and let the old maestro do his sniffing. Okay, here we are ready to go. The test subject is sequestered in the workshop. The cookies are waiting. Let's open the door. We know he's not going to base his choice on color because dogs don't see in color. Let's see what happens. I don't even think he sniffed the beef or bacon, but he picked the chicken. Okay, and then he goes back in the workshop to his normal nest to eat it. So chicken got the nod first. Next, let's see what happens when we wire capacitors in series and in parallel. And not only see what happens, but try to understand exactly why it happens. Before we continue, I think it would be helpful to review briefly a couple facts from part 1 of this series, and that is capacitance is directly related to the plate surface area. In other words, the larger the plate, the greater the capacitance. Also, the closer the plates are, the greater the capacitance. On the other side of the coin, the voltage rating is directly related to the distance between the plates. The further apart they are, the greater the voltage rating, and the resistance of the dielectric. Now that is not going to change, but plate size and distance should be kept in mind to understand how capacitance and the voltage ratings occur. So let's look at capacitors that are wired in parallel. In this case, the capacitance adds together, whereas the voltage rating will stay the same. That shadow that was cast is from Jack sitting in the window right behind me. Well, as you can see, the incoming current now has 2 choices. There's 2 separate routes. And at the end of each of these routes is a capacitor plate. So I think you can see that the plate area, the surface area of the capacitor plates, adds together. There's twice as much plate surface area. Recall then that that will increase the capacitance, and it does. The 20 and the 20 add up to 40 microfarads. However, the distance between the plates remains the same, so the voltage rating will remain the same. And since it's 450 for each of these capacitors, we end up then with a voltage rating for the pair wired in parallel at 450 volts. If you're wondering about the shadows which appear over the diagrams, it's because Jack, my able assistant, has been jumping up on the windowsill and looking out in the backyard. Now Jack, you better calm down, boy, because you're disrupting this presentation. And it's very obvious that he is obeying me. Next, let's look at what happens when we wire the same pair of capacitors in series rather than in parallel. In parallel, the incoming current had a choice of either capacitor, and whichever one they chose, the distance between the plates was fixed. In series, however, the incoming current is forced to pass through both capacitors. Therefore, the plate distance is no longer simply the distance of one capacitor, but also includes the distance between the plates of both capacitors. The plate area is going to stay the same. It's still a 20 microfarad capacitor plate area, but because the distance increases between the plates, we know that that reduces capacitance. In this case, 20 plus 20 will be reduced to 10 microfarads for the pair in series. And also we know that increasing the distance between the plates increases the voltage rating, so the 450 plus the 450 will add up to 900 working volts. Now, if you're wondering why this would be useful, one need look no further than the Fender Bassman amp circuit. Look here at the very first capacitance encountered by the B plus as it exits from the diode rectifiers. We have a 70 at 350 and a 70 at 350 wired in series. The net result is 70 plus 70 is 35 microfarads at 700 volts. Now, you know as well as I do, you can't find 700 volt capacitors very easily. So for just a few dollars, and by wiring a pair of very common electrolytic capacitors in series, here we will achieve the 35 microfarad capacitance that we seek at a whopping 700 working volts. Now, you're not limited to just 2 capacitors in series. You could have 3, 4, or 10 if you really wanted to have some astronomical working voltage. The net capacitance is calculated simply by putting the value of capacitance for each individual capacitor in the denominator with a 1 as the numerator, add them together, and the denominator of the sum will be the final net capacitance. All of which is confusing as heck, but let's look at real numbers. 1 over 30, 1 over 30, and 1 over 30, when we add them together, is 3. You add the numerators, the denominators stay the same. We can reduce this fraction to 1 over 10. And since the net capacitance is the denominator of the sum, we know that putting 3 30 microfarad capacitors in series will give us a final net capacitance of 10 microfarads. Now let's look at the voltage rating that will result from this trio of 30 microfarad capacitors all connected in series. Let's say that each one has an individual voltage rating of 350 volts. So we will add that together. 350 plus 350 is 700, plus 350 is 1050 volts, resulting then in the 3 capacitors in series producing a total capacitance at 10 microfarads at 1050 working volts. Okay, time for trial 2. In trial 1, he sniffed the sausage and took the chicken. I've replaced the missing chicken biscuit. Let's release our test subject and see what happens in trial number 2. Here he comes. Sniff the sausage. Sniff the chicken. Sniff the bacon. This time it's the bacon. And he's eating it on the spot. I think most people realize that capacitors actually discriminate between different frequencies. In other words, for a single capacitor, if you apply different AC frequencies to it, it will react in different ways to them. Now, why does this happen? Does the capacitor have a little brain with headphones on and it's listening to the frequency and it has sort of a built-in discriminating network? Not really. Actually, it's much simpler than that. And this discrimination is based upon an effect called capacitive reactance. Okay, it's nice, I think, to know the terms, but really to understand this, you don't even need to remember that term. Just remember what it means. Now we're going to cover the charging aspects of capacitors when confronted by AC and DC in just a few minutes. But for now, let's look at what happens when we apply a signal to a capacitor which has a frequency of 0 hertz, which we know is direct current. A little bit of current's going to flow here through this wire until the capacitor is completely charged, and then we will have a voltage existing across the capacitor of plus 12 volts on this side, minus 12 volts on that side, but no current is going to flow. Okay, so we know then that capacitors really detest or resist the passage of direct current. The lower the frequency, the more internal resistance, or better, the greater the capacitive reactance of the capacitor to that frequency. So low frequencies pass with much greater resistance than higher frequencies. So we can say that the internal resistance or capacitive reactance of the capacitor is indirectly related to the frequency. That may seem confusing, but it means that the arrows don't agree. If frequency is up, internal resistance is down. We have easy passage. Frequency is down, low frequency, then the internal resistance or capacitive reactance of the capacitor is high, and there will be very little passage. In a way, you could almost look at capacitors as potentiometers, with the rotation of the potentiometer based on the frequency of the incoming signal. High frequency, we're going to turn that volume way up and let it pass. Low frequency, we're going to turn that volume way down and hinder the passage. So although a properly functioning capacitor will exhibit infinitely high capacitive reactance to direct current, it will exhibit considerably lower capacitive reactance to alternating current. And as we will see, the amount of capacitive reactance it applies to that current depends on the frequency of the signal. Now, because with these videos we try to increase our level of sophistication a bit with each successive video, let's take a look at what seems like a really scary equation here, which is going to calculate a value for capacitive reactance in ohms for different frequencies. Now, capacitive reactance, which is generally symbolized by a capital X and a little c, is equal to 1 over 2 times pi, which is 3.1416, times the frequency in hertz, times the capacitance in farads. Now, farads, as we discussed in volume 1 of this series, is a huge value, and we generally are accustomed to microfarads and picofarads. Now let's perform a couple calculations using this formula, and I think we'll see it's really not all that tricky. Other than the conversion of our microfarads into farads, this is really just basic math. Let's use a 0.22 microfarad cap at 1,000 cycles per second, or 1 kilohertz. Okay, we'll say then that Xc, or capacitive reactance, is equal to 1 over 2 times pi, and I simplified it down to just 3.14, times 1,000 cycles per second, times the conversion of 0.22 microfarads into farads. And there are tables which will help you do this, but it ends up being 220 times 10 to the minus 9th farads. We multiply that out, and we see that the capacitive reactance for a 0.22 microfarad cap, when presented with a 1,000 cycle per second signal, is equivalent to 723.4 ohms of capacitive reactance. Now, this value in itself is not all that earth-shaking until we compare it to what happens when the same 0.22 microfarad cap encounters a signal that is not 1,000 cycles per second, but 20,000 cycles per second. Looking here at the math, the 2 remains the same, the 3.14 value for pi remains the same. Here the frequency is the only thing that's going to change. Up here it was 1,000 cycles per second. Down here it's 20,000 cycles per second. And the capacitance is identical when converted to farads. It's 220 times 10 to the minus 9 farads. When we plug all this into our calculator, we end up with a capacitive reactance value for a 20,000 cycle per second signal trying to pass through a 0.22 microfarad cap of only 36.2 ohms, dramatically lower than the capacitive reactance that was presented to the 1,000 cycle per second signal. To extend the potentiometer analogy to this, this is like we have in our tone circuit a potentiometer, which ranges from 36 ohms at the minimum up to 723 ohms at the maximum. When a 20K signal arrives, we turn the volume way up. We present almost no resistance, 36.2 ohms. But when that 1,000 cycle per second signal arrives, we crank the volume way down, presenting maximum resistance for that potentiometer of 723 ohms, and reduce it. So I think you can see how useful this would be for tone controls in our audio circuits. We can select different capacitors to allow different frequencies to pass. We can allow them to either pass to the next tube stage or to the output tubes, or we can allow them to pass to ground. Either way, we can very effectively control the frequencies in our input signal that are either helped or hampered. Okay, time for trial 3. So far he's sniffed the sausage, eaten the chicken, and eaten the bacon. The only one he hasn't picked is the beef. So let's unleash our star pupil from the workshop and watch him in action. Looked like he was starting to go for the beef. At least he's really considering them. Now you're confused? Pick a biscuit. Oh, the chicken again, eh? I think we're starting to see a trend here. Well, I think that does it for part 2. I'm going to try to keep these segments limited to around 20 minutes or less, which I think is about the attention span of normal humans. And we will pick up again in part 3, and I assure you that there will not be such a long delay before part 3 is posted. In part 3, we're going to go into detail about how capacitors charge and discharge, how they can actually shift the phase of the signals that are applied to them, and how electrolytic caps achieve the very unusual combination of high working voltage and high capacitance. Then finally we'll discuss how capacitors are used specifically in audio circuits, bringing together all of the details that we have learned and applying them to the circuit of the amplifiers we all know and love. So if that sounds interesting at all, then please stay tuned. We hope to see you again in part 3. Bye for now. Okay, I couldn't resist a fourth trial. I replaced the chicken, so he's picked it twice, sniffed the sausage, and eaten the bacon once. So it's 2 chickens, 1 bacon. This should be a very significant choice. Here comes our test subject. Well, I think this is pretty random personally. The beef didn't get much attention at all. So I'm just going to say that my theory that they're just the same biscuit in 4 different colors It's probably true. I guess the next thing I could do is taste them myself.